Hello students, this is our first lesson with Chapter 6 in Zumdahl, Thermochemistry. Thermochemistry is focused upon heat, hence thermo. We're going to be looking at the heat that is released or absorbed by chemical reactions, which usually accompanies every single chemical reaction. Before we can jump right into Chapter 6, we need some foundational terms. First, let's make sure that we are clear on energy. Energy is defined as the ability to do work. You probably recall that from 7th grade. However, more of the chemist's perspective is energy is the ability to produce or transfer heat, especially in terms of thermochemistry. The common unit for energy is a joule, capital J. An older unit is a calorie, lowercase c. The relationship between calories and joules is here. For every 1 calorie, it is equivalent to 4.184 joules. Reading any nutritional label, you'll see calories are also labeled. However, that is a capital C. So that actually, to our lowercase c, is a kilocalorie. So 1 capital C calorie is actually 1 kilocal, or 1,000 of our lowercase c calories. There are 2 general forms of energy, kinetic and potential. Kinetic is energy due to motion, 1/2 mv squared. Potential energy, energy due to position, but more importantly for us as chemists, energy due to composition. So what kind of energy do we have to invest to break chemical bonds, or what kind of energy is released when chemical bonds are formed? We know that matter, of course, is conserved, but so is energy. Energy is neither created nor destroyed. However, it can be converted from one form to another. For example, we know the common representative boulder rolling down a hill, that the higher it is above its lowest position, the greater its potential energy. But as it rolls down the hill, potential will convert into kinetic, one form to another. Now, we can trust that energy is always conserved. If you can use your imagination and imagine that boulder A collides with B, transferring energy and causing B to then roll up this small hill, we can see that B has not gained the same position in reference to the lowest position as A once did. Well, then do we lose energy? Well, energy can be converted from one form to another. Probably when they hit, some of the kinetic was transferred, energy of motion was transferred to sound. I'm sure there was some loss to friction, etc. All right. We are concerned with heat. So, do we know the difference between heat and temperature? Well, first, variables. Heat is represented by a lowercase q. Temperature with a capital T. Temperature is a measure of the average kinetic energy amongst your sample of matter. The average kinetic energy. And we know we use a thermometer to measure, and the units would be degrees Celsius or Kelvin. However, what about heat? Well, in contrast to temperature being the average kinetic energy amongst the particles in a sample of matter, heat is the sum total of the kinetic energy in the particles in a sample of matter. The total kinetic energy. Where we can directly measure temperature, we cannot directly measure heat. It must be calculated, and we will see how this is done. Truly, 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 the true worth of temperature is to be able to predict the direction of heat flow. That is the value truly of temperature. If you have 2 samples in contact with each other, whatever is at the higher temperature, let's say we have a sample of water that is at 50 degrees Celsius in contact with another sample of water that is 25 degrees Celsius, we can be sure that heat will flow from the higher temperature to the lower until an equivalent temperature, an equilibrium per se, is reached. Now, depending upon the quantity of your two samples and what the sample is, that will dictate what the final temperature of the entire mixture will be. But temperature truly exists to be able to predict the direction of heat flow. We can change the energy of a system either by changing the heat or by allowing the system to do work or the surroundings to do work on the system. Now, according to physics, work, lowercase w, is defined as a force that acts over a distance. So remember, work is force times distance. Now, how on earth can we get a chemical reaction to do work for us? Well, can we for a moment look at a syringe? Now, I think we saw with the unit assignment question from Chapter 5 with gases that we may be unfamiliar with what a piston is. So that's why I grabbed a syringe. I thought a syringe would best represent what happens with a piston. Now, if we consider the inner chamber to be our container, a piston is created when we have one edge that is movable. So it's not a rigid container. The volume can be changed. If we would heat the contents, we know that this gas will increase pressure and thereby increase the volume. So we have a movable wall, if you will, of our chamber. So a piston, which we see in car engines, which takes place in many of our machinery that we interact with on a daily basis, has one wall, if you will, in the container that is movable. So it is not a rigid, constant volume container. Well, we can have a reaction do work for us if it is a container over which we can have a change in volume. That's how we get a distance. And how does that change in volume happen? By moving the piston against an outside pressure. But we'll see more of this to come. All right, next. State function. A state function is a thermodynamic quantity, or a quantity that is pathway independent. Now, what does this mean? I live in Bethel Park, and each and every day I get myself to the high school. Now, I have a choice. I could take Route 19, or I could take McMurray Road. So you guys are familiar with McMurray Road, the curves, the very slow people you get behind, etc., etc., etc. If I take Route 19, well, that takes me by stoplights and so on and so on and so on, but I end up getting where I need to be at work. I start at home in the morning. However, my pathway can change. Now, from as far as my bosses are concerned, they could care less how I get to work. They know I started at home, that was my initial position, and I end at work, my final position. They could care less about the pathway. They just want me there on time. That is a state function. It doesn't matter what pathway you take. Just where did you end up versus where did you begin? Now, if we think about, changing volume, we often just care about that. Where do we end up versus where do we start? Volume is a state function. Pressure is a state function. Energy is a state function. But work and heat are not state functions. They are pathway independent. They are pathway independent. So, for example, my gasoline amount that I consume does depend on the pathway. So that's a good example of that. Okay, now we need to look at the term system versus the surroundings. We did a lab, our stoichiometric lab, looking at a calorimeter. So let's say we're doing a reaction and we have a closed calorimeter, double styrofoam cup. Well, usually our reaction, that's our focus. That is what we call the system. Everything outside of the reaction would be the surroundings, including the cup, including the classroom, including the building, including Murray, Pennsylvania, including the United States, etc., etc., etc. So our focus is per the system. And that is the perspective that we'll always be in, from the system's perspective. The rest of the universe would be considered the surroundings. All right, more terms. Exothermic and endothermic. Because we're dealing with heat, we know if our reaction releases heat, it's exothermic. If it absorbs heat, it is endothermic. Something that we need to get comfortable with are reaction diagrams. A reaction diagram looks at the progress of the reaction from start to finish and references the potential energy on the y-axis. At the start, we just have reactant, and at the end, we'll have our product. Now, our reactants, because of their bonds, are going to have a certain amount of compositional energy, a certain amount of potential energy. Well, through the progress of a reaction, if our products end at a lower energy position than we started, well, this amount of energy must be released in the process. This would be exothermic. And because we're always in the perspective of our system, per our system, it's losing heat. So Q would be negative. If our products end up at a higher energy position, potential energy, progress of reaction. This is my difference in energy. This is endothermic. I needed to invest energy into my system to get the products to be at a higher potential energy. This would be endothermic. And per the perspective of the system, Q is positive. Please watch the brief lesson 2 video to just continue and to get exposure to the first law of thermodynamics.